In this paper, we introduce a new hybrid Lagrangian-Eulerian simulation method called APIC. It is able to simulate a wide range of phenomena. Here we show a swirl of ice cream dispensed into a simulated cloth. We can also simulate water as seen in this flooding river. We can even simulate lava. Numerically, it is advantageous to use a grid for some computation and particles for others. This requires transferring between representations. Particle and cell, also known as PIC, is a simple method that transfers between particles and the grid. It does drop some modes only representable on particles, so it does act as a filter. Unfortunately, this results in very dissipative simulations. Flip alters the transfer by not acting as a strict filter and instead uses an incremental update. While this removes damping, the non-physics corrected particle modes lead to ringing instabilities. Note the particle velocities depict these modes. PIC and flip are often mixed to get the best of both worlds. This works to some extent. Even so, in this rotational example, while flip preserves rotation, any amount of flip mixture decimates the rotation. Thus, we are left with a trade-off between stability and low dissipation. Our method seeks to remove this trade-off. We first introduce a simpler, improved method called rigid PIC. It is stable like PIC while treating each particle motion as locally rigid instead of locally constant. While this works well on the simple rotation test, it fails when the simulation requires shear. To avoid this limitation, we switch from locally rigid particles to locally affine particles. We call this new method the affine particle and cell method, or APIC for short. APIC can handle shearing with no problem. It can also handle rotation without dissipation. Even on our original example, APIC is stable. In this 2D water example, we see that APIC better preserves vorticity. Now let's return to 3D. Consider this fountain animation. PIC improperly diminishes the width of the fountain. Even though flip does not do this, it suffers from noise. The flip mix also suffers from noise. Notice how the APIC is smooth and has the proper width. In the sand example, we also see that flip suffers from noise that APIC does not have. Notice how flip has escaped particles. Notice also the excessive mixing. Consider this jello simulation. PIC and mixtures of PIC with flip suffer from rotational damping. Full flip and APIC do not. However, if we zoom in, we can see that APIC is much less noisy than the flip simulation. We note that sometimes flip mixtures give interesting chunky behavior, as in this lava example. Even so, artists would tend to prefer to control chunkiness. In this sand example, we see that flip is unstable. Flip mixtures do work, but APIC gives a very nice dry sand result. Here we show two fireballs with large initial angular velocity colliding. Notice how APIC preserves this angular momentum and creates very interesting spiral patterns. The other methods do not. They dampen significantly or have too much noise. Here we show just the APIC result with a black background to make a more dramatic shot. To celebrate the introduction of our method, we decided to pour some glasses of wine. Here we show a comparison between apic blends and flip blends. In the flip blends, we see that the flip 1 is rather noisy and doesn't create a nice surface. Once we blend down to flip 0, we actually get pick and it's too dissipative. If we look at the apic blends, we see that a nice shape is preserved even on apic 1, and it actually is so energetic that it overflows the glass. Fortunately, we've anticipated this eventuality, and we have some towels to clean up the mess.